Hello everyone, welcome to this lecture on the Heaviside step function. This lecture is a part of module 2 of your course in Mathematical Physics 3, and it follows from the previous lecture on the Dirac delta function. So in this lecture we will briefly touch upon what a Heaviside step function is and how to find out the derivative of this step function, and then finally we'll end with some operations, some basic operations on this function. Now just like to clarify something over here. That is the Heaviside step function, even though we have used the word function here, and the same thing holds good for the Dirac delta function also. Even though we have used the word function here, but to be more accurate, we should really be using the word distribution, because it is not really a function, it is a distribution. Now I would not be going further in details into what exactly a distribution is, because that itself is a topic by itself. But for at present, it'll just suffice if I mention that distribution is it encompasses the concept of a function. So basically, to put it very simply, we call something as a distribution a mapping. Okay, for instance, a mapping from one set to another set, we call it as a distribution if it also encompasses infinite sequences which converge in some way or another. And we have seen in the previous lecture on the Dirac delta function that the Dirac delta function can be expressed as a limit of a sequence of certain functions. So that makes the Dirac delta function a distribution. And the same thing holds good for the Heaviside step function as well. It can also be expressed as some kind of a approximation to a function, and if you take that to a certain limit, then it gives us a very good approximation of the Heaviside step function. So it is actually a distribution that we are talking about here. So first of all, the Heaviside step function, we denote it by capital H, or by theta, or by U. In this lesson, I'll be sticking to this symbol. I'll be using h of t as the symbol for the Heaviside step function, even though in certain books and certain websites you might be finding this symbol also. Okay, so any of these could be used to denote the Heaviside step function. It's a very interesting function. It helps us to come up with an idealized representation of certain physical phenomena. So it's basically it's a piecewise constant function. Okay, so it's a piecewise constant function which takes the value 0 if the argument is negative. That is, here when I write h of t, the argument is t. So if the argument t is negative, this function will take the value 0. But if the argument, that is t, whatever is inside the bracket, if it is positive, then this Heaviside step function will take the value 1. So we could define it this way. So for negative values, it's a mistake over here. It should be t here. I had mistakenly written here as x. So please read this as t. Okay, so as if for t less than 0, the Heaviside step function takes the value 0. For t greater than 0, that is positive values of t, the Heaviside step function takes the value 1. Then what is the value at t equal to 0? We can take this as half. Okay, in fact this is the definition that I had got from that I just picked up from Wolfram Math World. The reference is there at the end. So at t equal to 0, we could take the value to be equal to half, and graphically we can represent it like this. Okay, for negative values of t it takes 0, and for positive values of t it takes the value 1, and then there is a extremely vertical line which joins these two points. Okay, and this passes through the point half. Okay, so we can take the value of the Heaviside step function at t equal to 0 to be equal to half. Now, the Dirac delta function, if you remember, what was it used for? It was introduced by Paul Dirac to to give us an idealized picture of, say, a point distribution, say a point mass or a point charge. So, in a similar way, the Heaviside step function could be used to represent, say, for instance, let's say I have a switch in an electrical circuit. Let's say I have a switch. The switch is initially off, and then I suddenly put it on, right? So it suddenly changes state from zero, from off state it changes to on state. So suddenly from zero there is a sharp increase, and then it goes to 1. Okay, so that kind of a step can be represented using a Heaviside step function. You might recall that in the previous semester, in your practical using Scilab, we had done some experiments using XCOS, some simulation experiments using XCOS, and over there we had used a step function to represent the fact that we are putting on. For instance, if you remember the damped oscillator problem that we had done in XCOS, over there we had used something like a step function which was used to represent the fact that we are putting on the oscillator at a certain point of time. So this is an application of the Heaviside step function in electrical circuits. Another place where the Heaviside step function could be used is in, say, quantum mechanics, where we are trying to model a step potential. Okay, so a step potential can be modeled using a Heaviside step function like this. So we could now talk about the derivative of the Heaviside step function. Here we can get some ideas as to what to expect. Okay, what kind of derivative do we expect? Okay, so if you look at the graph of the Heaviside step function and you recall the concept from your basic calculus, that what exactly is a derivative? Derivative is basically the slope, okay, the slope of the tangent that you draw at each and every point on the curve. Now here, if the slope that is, if the tangent is horizontal, then the slope is going to be 0, and if the tangent is vertical, then the slope is going to be, it's going to tend towards infinity. So now if you look at this graph of the Heaviside step function, so what kind of derivative do we expect? Okay, so our expectation is basically this. For positive values, okay, for positive values of t, we expect the derivative to be 0. Why? Because for positive values, you see the graph, it's a horizontal line, and the derivative of horizontal curve is going to be always 0. So the derivative of the Heaviside step function in this part will be 0. Same thing will happen for the negative values of t also. For the negative values of t, the derivative of the Heaviside step function again will be 0. But what will happen at t equal to 0? At t equal to 0, what happens is the graph becomes almost vertical. So if the graph becomes almost vertical, then its slope will tend towards infinity. Okay, so at t equal to 0, the derivative will tend towards infinity. So for positive values of t, the derivative of the Heaviside step function is 0. For negative values of t, the derivative of the Heaviside step function is also 0, and for t equal to 0, the Heaviside step function, its slope, okay, the slope is nothing but a derivative. The derivative will tend towards infinity. Now when we look at it, you immediately recall that this is nothing but the distribution for the Dirac delta. This is nothing but the Dirac delta distribution. So it suggests that the Heaviside, if you differentiate the Heaviside step function, you should get the Dirac delta function, or to be mathematically correct, what I should say is the derivative, the distributional derivative of the Heaviside step distribution is nothing but the Dirac delta distribution. Now, but this is just we are just speculating that this is how it will be, but we can actually derive and we can arrive at this particular fact. So what we do is we take any arbitrary function, let's say any arbitrary function f of t, okay, and taking this arbitrary function, let us consider this integral. So we are trying to integrate the product of that arbitrary function with the derivative of the Heaviside step function. Now what will that give us? We can just apply the integration by parts formula here. So we are having a product of two functions. In this integral, we are having the derivative of one function and the other function as it is. So on the other side, we will have the product of the two functions as they are, evaluated at the two limits, that is minus infinity and plus infinity, minus again the same integral but the derivative symbol being swapped. Instead of h prime we'll have to use f prime. So f and h prime, so we just take the functions f and h as it is, take the product of that, and we evaluate it at minus infinity and plus infinity, minus the same integration except this prime goes to f, and we have this. So this is basically nothing but your integration by parts. So now we need to evaluate this one. So when we evaluate this, we'll get f evaluated at infinity. Why do we get f evaluated at infinity? Because when we substitute the values here, we have f infinity, the lower limit is f in infinity, h infinity. And what is f minus infinity and h minus infinity? What is h minus infinity? At negative values of t, the Heaviside step function takes the value 0. So h minus infinity will be 0. So at h plus infinity, that value of the Heaviside step function will be 1. So as a result, we'll have f of infinity. That is what will be left from the first term. And in the second term, what we do is we split this up. So instead of integrating from minus infinity to plus infinity, we first integrate from minus infinity till 0, then we integrate from 0 to infinity. Okay, so here again we use the same, we use the property of the Heaviside step function for negative values of t. Okay, so this is the integration over the negative values of t. For negative values of t, the Heaviside step function takes the value 0, and for positive values of t, the Heaviside step function takes the value 1. So as a result, this is going to vanish, and finally we'll have this. What are you trying to do? We are trying to integrate the derivative of a function. Integration of the derivative of the function will leave the function unchanged, and so we'll be left with, we just have to evaluate the function at the upper limit and the lower limit. So this will give us f at infinity minus f at 0. So these two will get cancelled. So this will give us the integration of this quantity, this product of f and the derivative of h is equal to the value of the function at 0. So let's call this equation number 1. Now if you recall, in the previous lecture we talked about the fundamental defining property of the Dirac delta distribution. Okay, the fundamental defining property is basically this. So if I integrate any function, okay, any arbitrary function multiplied with the Dirac delta distribution, and you integrate from minus infinity to plus infinity, that is nothing but the value of the function which is evaluated at point A. This is the property which defines the Dirac delta function. So now if I put a equal to 0, okay, if I put a equal to 0, this is what I'll get, because a equal to 0 we have f of t, delta of t, dt, and here a we put 0, here we have f of 0. Now if you compare these two equations 1 and 2, okay, so f of t is just the same here. The right hand side we have f evaluated as 0. That means in the integrand, this part, that is h prime and delta t must be equal. So this gives us that the derivative or rather I should say the distributional derivative of the Heaviside step function is indeed equal to the Dirac delta distribution. Okay, so now we could have many different orientations. Now it's just a time to have some fun with the Heaviside step function. So we could just reorient the Heaviside step function in many different ways. Okay, so what we basically do here is this. I'll take the Heaviside step function. Okay, I'll take the Heaviside step function, and I'll just I'll displace it by a certain amount, say by an amount a. Then we have two things. One is the sign of the function, another is the sign of the argument. So just by swapping the plus minus sign outside as well as inside, then we'll be able to get 4 different orientations of the Heaviside step function. That is, we will first put a minus sign outside, then we'll put a minus sign inside. That means outside means outside the function. Then we'll put a minus sign inside the function, that is on the argument of the function. Okay, so we will have 4 different possibilities. So that will give us 4 different orientations of the Heaviside function. So first we have this. So we have h of t minus a. Okay, so like I said, the definition of the Heaviside function is wherever the argument, if the argument is positive, okay, the argument of the Heaviside function, if it is positive, then it will take the value 1. If the argument is negative, it will take the value 0. So argument, what is the argument here? Argument is t minus a. So in this case, if t minus a is greater than 0, Okay, if it is positive, t minus a is greater than 0, then this will take the value 1. So t minus a greater than 0 means t is greater than a. So whenever t takes the value greater than a, okay, that is this point is a. So in this example, in this graph, a is equal to, here this is 1 and this is 2, a is equal to 1.5. So this graph is basically h of t minus 1.5. Okay, so if I put a equal to 1.5 here, this is the graph that I'll get. So t minus a greater than 0, that is t greater than 0. Okay, sorry, t minus a greater than 0, that is t is greater than a. For those points, this function will take the value plus 1. T minus a less than 0, that is t less than a, that is t, in this case t less than 1.5, it will take the value 0. So essentially, if I don't put, if a equal to 0, then this transition, this discontinuity will happen at the origin. But if I put t minus a, okay, a is some quantity, okay, it could be positive or it could be negative. So if I write as t minus a, then accordingly the discontinuity will occur over there. So if I put here, in this case, a is equal to 1.5, okay, so that means the discontinuity from 0 till 1, that step, where does it take place? It takes place at 1.5. But if I put a equal to minus 2.5, then here we'll have h of minus 2.5, it will give us h plus 2.5. h plus 2.5, moment you have a plus sign here, then that means you have to go here. So this is where the step will take place. Okay, so in general we just consider it as h of t minus a, then whatever is the a value, you just substitute here. Accordingly you will be able to obtain the Heaviside step function. So we have h of t minus a, so all it does is it just shifts t minus a, it just shifts it to the step at point a. Now what we do is I put a minus sign in front. Okay, the moment I put minus sign in front, what happens is the function, wherever the function was taking positive value, it will take negative value and vice versa. In this case, the Heaviside step function does not take any negative values, it only takes positive values. Okay, it takes the positive values here, that is when t is greater than a, it takes positive values. So when I put minus h of t minus a, wherever t is greater than a, instead of taking 1, it will take the value minus 1. So in this case, a is equal to 1.5. So for t greater than 1.5, minus h t minus a will take minus 1 value, and for lesser t less than a, it will take the value 0, just the same as before. So here how did we go from here to here? From this function, from this distribution till this distribution, the way we went was we just put a minus sign in front. Okay, we just put a minus sign in front, it just caused the negation. Okay, now what if instead of putting the minus sign outside the function, what if I put a minus sign inside the argument? Okay, in the argument. So that means if I put a minus sign over here, so it will give us minus t, minus and minus will get plus, so minus t plus a, minus t plus a. In that case, what will happen is wherever it was 0 earlier, okay, these points, wherever it was 0 earlier, those points will now take the value 1, and wherever it was it was 1, those points will take the value 0. Okay, the point where this happens, it is still a. Here at a there was a step, and here also at a this will have the particular step. So this is what happens. So if you put a minus sign in front of the h of t minus a, you will get a distribution like this. If you put minus sign in the argument, then you will get the distribution will change to be and become like this. Now what will happen if I put minus outside as well as inside? Then this will be the case. I put a minus sign outside and a minus sign inside. So minus sign outside, what it will do is, so essentially what am I doing is, already we have a minus side inside in this case. Now all I need to do is just put a minus side here, that will give me this function. So what will happen is, wherever it is positive, the positive parts will become negative, the 0 parts will remain the same. So you can see here this part remains the same, this positive, it was plus 1 here, it becomes minus 1 here. So this is one more orientation. So 4 different orientations of the Heaviside function. How do we get these orientations? Just look at the signs, okay, outside and as well as inside. Here the sign is positive, here also you take it as overall there is a positive sign, so plus plus. Then we put this one we get it as, we put a minus sign inside, so plus minus inside. Then we have a minus outside and a plus inside, and then we have minus outside and minus inside. So this will give us these 4 orientations, and you can notice here in all the 4 orientations the step always takes place at a. So this is in all the cases a is this a is 1.5. So here at 1.5 there is a transition from 0 to 1. Here at 1.5 again there is a transition from 1 to 0. Here at 1.5 there is a transition from 0 to -1. Again here at 1.5 there is a transition from -1 to 0. So these are different orientations. Next, another interesting application of the Heaviside step function is we could when we try to take the difference of two different Heaviside step functions. Let me show you how. So consider the following Heaviside functions. So let us say I have h of t minus a given by this, okay, as usual. Okay, so this is h of t minus a, that is here in this example this is 1 here, that means a is 1. Just to give a feel for this, a is 1. So we have this to be the distribution. So h of t minus a, that means the Heaviside step function will shift towards the right side and the step will now take place at 1. Now consider another distribution. Okay, so over here one function is h of t minus a, another function is h of t minus b. Okay, so here b in this example, b is, this is 2 and this is 3, b is somewhere in between, so it is b is around 2.5. okay, so here h of t minus a, it goes from 0 to 1 at a equal to 1, and h of t minus b, it goes from 0 to 1 at b equal to 2.5. okay, so this is where the step will occur. So remember this, when t is less than a, okay, when t is less than a, this function will be 0 and this function also will be 0. When t is greater than a, this function will be 1, and when t is greater than b, this function will be greater than will be equal to 1. And in this example I'm assuming that a is less than b. Okay, so a here is 1 and b is 2.5, so a is less than b here. Okay, so now let's evaluate the difference. I want to find out h of t minus a minus h of t minus b. What will be the difference of this function minus this distribution minus this distribution? Let's try to find out the difference between the two. So we will evaluate them one by one. For t less than a, we will take this range. Okay, this is a. Okay, this point is a. For values of t which are less than a, okay, if you look here, this is h of t minus a. For values which are less than, for t less than a, h of t minus a is 0. And where is, what is a here? A is this, because a is less than b. In h of t minus b also the function is equal to 0. So h of t minus a and h of t minus b, it will be 0 for t less than a. Okay, so therefore if I take the difference h of t minus a minus h of t minus b, h of t minus a minus h of t minus b, it will be 0 minus 0, the value will be equal to 0. Okay, now let's take the next part. Okay, so next part will be for values of t which are greater than a but less than b. Okay, the values of t which are greater than a but less than b. For values of t which are greater than a means the first function h of t minus a, it will take the value 1, but it is still less than b. Because it is less than b, h of t minus b, this will be 0. So h of t minus a will be 1, h of t minus b will be 0. So 1 minus 0, the value will be equal to 1. Okay, so for values from 1 to 2.5, as in this example, the difference between these two, h of t minus a minus h of t minus b, that is going to give us the value 1. And finally, for t greater than b, b is 2.5 here. For t greater than b, h of t minus a will be 1, but here again h of t minus b, this will also be 1. So both will take the values 1. This will also be 1, this will also be 1. So since both are 1, when you take the difference between them, they will become 0. Okay, so you can see the difference here for this range of values. For values which are less than a, the difference between them will be 0. For values which lie between a and b, the difference between them will be 1. For values which lies greater, for values which are greater than b, the difference between them, again it will become 0. So 0, 1 and 0. Okay, so from equations 1, 2 and 3, this is what we get, the difference between them. For t less than a, it will be 0. For t lying between a and b, it will be 1. For t greater than b, again it will become 0. So this is how it is going to look like. Okay, so difference between these two functions will give me something like this. Okay, so this is in quantum mechanics we encounter this is as a barrier potential. Okay, this is a barrier potential. Okay, so when we have this tunneling effect, those kind of problems, the tunneling effect of electrons, over there we encounter the barrier potential. So this can be represented, the barrier potential can be represented as a difference of two Heaviside functions. Okay. All right, so now next interesting application is the sampling of function regions. So suppose I have a function, okay, and this function is well defined in a range which contains the value a. Okay, so it is well defined in a range, and in that range this value a is also there. Then I could sample the value of the function over any sub interval. Okay, so let's say for t less than a, okay, for t less than a, what will this be? The product of the function and h of t minus a. Now we know that h of t minus a, okay, the argument is t minus a. This is a Heaviside step function. It takes the value whenever the argument is negative. Argument is t minus a. T minus a is negative, means t minus a is less than 0, that is t is less than a. For t less than a, this will take the value 0, so this will be 0, and as a result the function will take the value, the product of these two will always take the value 0. But for t greater than a, again what will happen? T minus a, Heaviside step function, the argument is positive. Argument is positive means t minus a is greater than 0, that is t is greater than a. T is greater than a, it will take the value 1. Okay, so f of t into 1, it will give me the function itself. So if I take a product of a function with h of t minus a, f of t multiplied with h of t minus a, then for all values of t which are greater than a, for all values of t which are for all values of t which are less than a, the function, this product will give us 0. But for all values of t which are greater than a, we will get the function. Okay, so we could write it like this: the product, it's a continuous function. Moment I multiply this with h of t minus a, I have converted a continuous function into a step function, and the discontinuity takes place at t equal to a. Okay, for t less than a, it will be 0. For t greater than a, it will be f of t. It will be the nothing but the function itself. So an example of that could be we have a step function here. Okay, Heaviside step function. The a is equal to 0.5. Okay, a is equal to 0.5 here. So at 0.5 we'll have a step from 0 till 1, and this is the function f of t. It's a well defined function. Okay, in fact actually this is a Gaussian distribution. Okay, so now if I multiply this function with this, then at a, okay, at a, for all values at a, okay, for all values of t which are less than a, we have 0 here. So from here, this is a. For all values which are lesser than that, this entire thing, the product, it is going to become 0. So we'll have zeros everywhere here. For values which are greater than a, okay, the function will remain as it is. So we'll have the same values as the function itself at a. Okay, so we'll have the same function itself for t greater than a. Another example is this one. So here this was a product of the Heaviside step function with a Gaussian distribution. So again here I take a Heaviside step function. Now the step is taking place at minus 2.5. This is minus 3 and this is minus 2. This is minus 2.5. So this function can be written as h of t minus 2.5, which is h of t plus 2.5. So this is the step function. This is okay, this is nothing but f of t equal to t square. Okay, this is just the parabola. So this is f of t is equal to t square, and when I multiply these two, what will happen is here from less than minus 2.5, less than minus 2.5, the values are going to be all zeros. For t greater than minus 2.5, the values will be same as the function itself. Okay, so this is how we can convert continuous functions into step functions, discontinuous functions. Then in a similar manner, so here what we did was we multiplied the function with the Heaviside step function. So one side we had 0, and on the other side, one side we had 0 and the other side we had the function itself. Now we could also, what you could do is, we could, instead of multiplying the function with a single Heaviside step function, we could also multiply it with a difference of two Heaviside step functions wherein a is less than b. Now you know what will happen here, because if you remember, forget about this f of t. When you don't put this f of t, h of t minus a minus h of t minus b will be the same thing, except here there will be a 1. Okay, and since you are multiplying f of t, this will remain 0, this will remain 0, so 1 into f of t, so we'll have a f of t here. So here we are able to sample the function within a certain interval. Okay, so let's say I take a value here. So in this case, a is, this is 2 and this is 3, a is 2.5, and b is, this is 3, this is 4, b is 3.5. So a is 2.5, b is 3.5, a is less than b, and we'll get a step potential, something like this. Okay, so yeah, again I take this same parabola, okay, f of t equal to t square, and when I multiply them, what will happen is, wherever this this function, okay, wherever it is 0, it is 0 here. Okay, this region also it will be 0, and this region we have zeros, so here also we'll have zeros. Only within this region between 2.5 and 3.5, between 2.5 and 3.5, we will have the function taking this product, taking the same value as the function itself. So likewise, like this, we can actually sample different regions of the function itself. Okay, this is again the same thing. We have taken that, instead of the parabola, we have taken the Gaussian distribution as before, and just multiply this with a difference of these two Heaviside step functions. So here is somewhere, I think it is 0.2, a is 0.2 and b is 1.2, and we will get the product of them. Okay, so from here till here, so that is where it will be equal to f of t, else everywhere it will be 0. So I think I'm going to stop here. Okay, this is that's all I would like to discuss regarding the Heaviside step function. I will not be doing the approximations, okay, because like I said, it's a distribution, so it can be, the Heaviside step function can be expressed as a limit of a certain sequence, just like the Dirac delta function. Okay, so in the previous lecture we had approximated the Dirac delta function as a limit of a certain function of harmonics, but we can do that something similar for the Heaviside step function also, but I'll not be doing that, because that is out of the scope for your syllabus. Maybe in some other lectures, maybe at a later time, I could just include that. So all these plots that I have shown you in this particular lecture, all these plots, these are just simulations using Scilab. Okay, so you can just feel free to actually try them out on your own. In fact, one of the exercises that I have given you, actually it asks you to do the Scilab coding for the same. Okay, so we'll stop here. Finally we come to the exercises from this lesson. So this is one problem that I would like to just try out. I would like you all to just try it out. There is a function, there is another special, there is a discontinuous function which is known as the signum function. Okay, this is how a signum function looks like. What the signum function does is, again, it's not really a function, it's a distribution. What it does is, for positive values of t, that means whatever is the argument, wherever the argument is positive, the signum function takes the value 1. Wherever the argument is negative, the signum function takes the value -1. So it is just like the Heaviside step function, except instead of having 0 for negative values of t, it takes the value of -1. And at t equal to 0, we can consider the signum function to take the value 0. Okay, so you can see here, this is very similar to the Heaviside step function, but except instead of 0 here, it takes the value -1. So the question, you have to basically prove these two. We have to show that the signum function can be written as the difference between two Heaviside step functions. One Heaviside step function is h of t, and the other Heaviside step function is h of -t. Now if you recall here, look at the hint is, you look at the discussion on the orientations of the Heaviside step function. So here what have I done? I have put a minus side inside, right? I have put a minus side inside on the argument of the Heaviside step function. So that will give you as to what is the orientation, and from there you can actually prove very easily, you can show this. Then the other thing is you have to show, after you have shown this, you have to show that I mean, this is how, this the first part is you can write a signum function in terms of the Heaviside step function like this. Alternatively, you can also express the Heaviside step function as the signum function like this. So these are the two things that you'll have to show. So that's your first exercise. Then the second exercise, it's really fun. All you have to do is you have to just sketch these. Okay, so this combination, so we have a combination of two Heaviside step functions. You just need to draw how it will look like. Similarly, this is a combination of two Heaviside step functions. Just draw how the combination looks like. Now this is a combination of three Heaviside step functions, so just extend the ideas. I mean, we have already done this. Okay, so you have to proceed in this manner. So let me, yeah, the steps that we had followed. Okay, so we just took the difference of 2 and then we got this in a similar way, and we got this kind of a distribution. So we have to proceed in a similar way to draw the sketch for these combinations. Now the third and the fourth exercises in questions in the second exercise, instead of two Heaviside step functions, we have three Heaviside step functions. Okay, please follow in the same way. You just have to divide the t, all the values of t. You just have entire range of t, you have to just divide between certain sub intervals, and each of the sub intervals you have to just evaluate them separately. So that will help you to sketch this. Okay, then okay, I'm sorry, this will be question number 3. I'll correct them in the assignment that I'll provide to you. In the third exercise, what you have is you have to express the following piecewise distributions in terms of the Heaviside step function. So that is f of t. It's not a continuous function, it is a piecewise continuous distribution. So f of t for modulus t greater than 2. I'll leave it to you how to figure out what this really means. Whenever modulus of t is greater than 2, it takes the value t cube, otherwise it takes the value 0. So how will you express this kind of a distribution using the Heaviside step function? Or it need not be one single Heaviside step function, you could have a combination of Heaviside step functions also. Then same thing for this one. This is a exponential e to the power minus lambda. Okay, in all the cases b, c, d and e, in the remaining 4 cases, please assume this lambda to be a positive quantity. Okay, so please try this out. You have to just express this, okay, in terms of these piecewise continuous distributions in terms of the Heaviside step function. And lastly, this is optional, but it'll be fun if you can try that. Please try to write Scilab functions which plot the same thing, just along these lines. Okay, so that's how I had given here. I'll provide you the code, okay, for these whatever I have done in this particular lecture. I'll provide you the code just like the last time. Please try to write Scilab programs which do the same thing. Okay, so with this we come to the end of this lecture. So these are the references. This is a really good article. It's a very short article. You could go through this as well as the Wikipedia page. So in the next lecture we will be discussing we will be starting with the goal of the next lecture will be convolution, and over there we will be applying all these results. Okay, so it's very important that you finish these. So these results will be applying, and we will be obtaining some more interesting results. That is, we'll be trying to find out the Fourier distribution, the Fourier transform of, let's say, the signum function, or the Fourier transform of the Heaviside unit step function. So we can find out all of that using these distributions. So it's really important that you finish this. Okay, so please do this so that we can be ready for the next lecture on on the convolution theorem. So with this we come to the end of this lecture. In case you have any queries, please feel free to reach out to me. Thank you.